Hello, this is Mr. Gilmore with the 9.3, the arc-chord theorems. Now today we're going to actually look at a number of fundamental relationships that chords have with arcs. Let's dive into a little bit of review about what an arc is and what a chord is. If you remember, an arc is really a portion of a circle's circumference. Imagine with me, you place 2 points then on a circle, and then as you follow the path from one point to the other, you really are following then the path of an arc. Now, a chord is where if you place 2 points on a circle and you walk the straight path from one point to the other, that chord is the segment then whose endpoints are points on the circle. So in the diagram below, we have our circle A such that we've placed 2 points on the circle B and C. If we follow the curve path, we're actually looking at then the arc, right, from point B to point C. As we follow the circle's path, we follow then the arc. However, if we were to follow straight from B to C along the segment length, we're actually then following the chord BC. One other quick review before we move into our first set of theorems is the central angle. Keep in mind, remember, that the central angle cuts an arc. And we've already seen the relationships that central angles have with the arcs that they cut. That, in fact, that by definition of arc measure, that if we have the measure of the central angle, then the measure of the arc is equal to that same measure. So in our example below, we see that our central angle BAC has a measure of 88 degrees. That means the measure of the arc BC also has the measure of 88 degrees. What we also then proved in the last lesson, 9.2, we saw that the measure of central angles, we can actually prove a couple of other things with them, such that if we're given two central angles that are of equal measure, then we know they cut arcs of equal measure as well. And that's one of the theorems we're actually going to reference in one of our first proofs today. Let's dive into one of our very first theorems today. Now, this theorem doesn't technically have a name to it. We'll see that most of these Chapter 9 theorems don't have names. They're just going to simply be referred to as the theorem number on the postulate theorem handout, or you'll be using them in reference to what they actually do. So the title of our slide here, Equal Chords Cut Equal Arcs, that's really what this theorem is going to explain for us. That is, if we're given chords of equal length, then they actually will cut arcs of equal measure. So if we take a look then at our diagram below, we're given our circle A such that we are given these two chords B, C, and D, E. And we're actually given that those two chords are already equal in measure, meaning the lengths of those two chords are equal in length. What we're going to prove then is that each of those two chords actually cut an arc, right? BC cuts the arc BC and the chord DE cuts the arc DE. We're going to prove that the measure of each of those two arcs are actually equal to each other. Let's take a look at this proof together. So the proof, we have our same diagram, circle A. We've got our two segments in there, two chords, I should say, BC and DE. And we're going to prove that the measure of arc BC is equal to the measure of arc DE. Now, where do we start is actually with a construction phase. Because in our diagram here, we want to begin relating some information that we've already studied from past chapters with our current information here with circles. So what we're going to do is we're going to connect point A to point B, point A to point C, point A to point D, and point A to point E. And what we form then is a set of triangles, a pair of triangles. And as it turns out, we're going to be able to prove that those two triangles are actually congruent to each other. So if we take a look, we know right off the bat from our given that BC and DE are equal. But we just actually formed four additional segments, AB, AC, AD, and AE. As it turns out, those four additional segments are radii of the same circle, which means by definition of radius, we know all four of those segments are equal to each other. But in other words, what we know more about these two triangles is that all three sides of one are now equal to all three sides of the other. What that leads us then to say is that triangle ABC and triangle ADE are actually congruent to each other. That's what we see there in step 4. What that means now with our congruent triangles, we know all their corresponding angles must be equal. So what we're then going to say here is that we know that angle BAC is equal to angle DAE. These two central angles there are equal. And because those two central angles now are equal, we can then say that they cut the arcs of equal measure. That was actually a theorem we proved in the last lesson. So I can claim now the measure of arc BC is equal to the measure of arc DE. And my reasoning there, notice that I had to kind of write out or type out what the reason was because that theorem didn't have a name. So I typed out what that theorem did. Equal central angles cut equal arcs. So that's what I said there, right? Because I have equal pair of central angles, which means they cut those equal pair of arcs. Now, as it turns out, that this theorem actually has a true converse, which means when you get the worksheet, not only are you going to see this proof on the worksheet, I'm asking you to repeat, but you'll actually see the converse of this theorem as well. And so using what we've seen here in this proof, use it as a little bit of guidance to say, oh, what I'm looking for then are a pair of congruent triangles. And you'll look for the exact same thing in the converse of the proof. Let's move on to our next theorem. This theorem, again, doesn't have a title, but we're going to go off of what it does. So the title slide of this one says diameters perpendicular to chords bisect them. So let's take a look at the conditional. If a diameter or a radius is perpendicular to a chord, then it bisects that chord and the arc that it cuts. In other words, let's take a look at our diagram and let's unfold what this conditional is actually really saying. So in the diagram, we're actually given two pieces of information. First off, I did leave quite a bit out of our given just because it would be a whole lot in that given. Let's just boil it down to some of the initial thoughts that we need for this. So what we're actually given is a diameter BC. We're also given a non-diameter chord, EF. And what we're going to find is that we're given BC is actually perpendicular to that chord EF. We're actually going to prove two things then about this relationship with this non-diameter chord and the diameter BC. We're first going to prove that it bisects that chord. In other words, that the length of ED is going to be equal to the length of DF. So essentially, we can prove that D is the midpoint of that chord there. The other thing we can prove is that point B is really going to be the midpoint of that arc, where we have traveling from path E to F with the chord or with the arc EF. EB will then, the measure of EB will equal the measure of the arc BF, and that's a second thing we'll be able to prove, and we can prove those we can prove them very quickly, actually. We're going to prove ED equals DF first, and then right after that, we'll grab the fact that BE, the measure of arc BE and the measure of arc BF will be equal as well. So let's take a look at that proof together. So we are given, again, from the beginning, and again, I've left out a couple things, piece of information are given, such that we know BC to be a diameter. We also know EF is a non-diameter chord. Okay, so we know BC is perpendicular to EF, right? So we're given that we have those right angle already there in our diagram. What we're going to do is, again, in our second step here, is form some additional segments. So we're going to have a construction phase. That construction phase, I'm simply just going to take point A and connect it to point E, and then I'm going to take point A and connect it to point F. What I formed there is a pair of radii, and because I have those two radii, I know of the same circle that they must be equal in length. So I know that AE is equal to AF. What I'm working toward is actually proving that I have a pair of congruent triangles in this diagram now. Because these two triangles actually share a side AD, they have that common side there, and I know that because BC is perpendicular to EF, we know that those must then be right triangles. Because of that, with our equal sides AE and AF, our equal side AD by reflexivity, what we really have there is the special congruence case of HL, hypotenuse leg, because AE and AF are really the hypotenuses of the right triangles. AD is the common side, which is actually an equal pair of legs, and of course with the given BC's perpendicular to EF, we know then there are right triangles. So in step 5, we can declare those triangles actually congruent to each other. ADE is congruent to triangle ADF, and that gives us actually our first piece of information that we want to prove, which is that ED is equal to DF, and we know that because of our good friend CPCTC. So we grab that in step 6, the first part, but then we also grab an equal pair of angles. Let me explain why we're doing this. We're going to grab that we know BAE is equal to BAF. These two angles down here are equal because they are corresponding of those two triangles. Now, because we know that those two angles are equal, they are central angles, which means if we have an equal pair of central angles, they cut arcs of equal measure. So we can then claim in step 7, our last little statement that we wanted, which is that we know the measure of our arc BE is actually equal to the measure of our arc BF, because again, that theorem doesn't have a name, so I just write out what it does. That theorem says that equal central angles cut equal arcs. And so there we have it. We reach both conclusions to this perpendicular diameters bisect chords theorem. Now, this theorem, this perpendicular diameters bisect chords, also has a true converse, which means what you'll be seeing on the worksheet is a second theorem that comes alongside with this one that says you're going to be given that BC passes through EF such that it bisects EF, so it's given that it bisects EF, you're going to prove that it's actually perpendicular. So you're going to prove the converse of that. And again, you're going to approach it from a similar point of view of you're going to draw in some extra radii, you're going to find triangles, you're going to prove those triangles will be congruent, and then you can use that to arrive to your conclusion that those two segments would have to then be perpendicular to each other. Before we move into our very last set of theorems here, let's take a look at two quick postulates. Now, we really already have these postulates laying around. We can really tuck them into the um, quotient, using the division property and using the multiplication property. That's where we actually can develop both of these postulates. So let me go ahead and break these two down for you real quick, because we are going to use them in our last set of theorems. So the first postulate is simple. It's halves of equals are equal. Essentially, if I were to give you two segments of equal length, right? You've got two segments of equal length. So if AB is equal to CD, and M is the midpoint of one segment, right, AB, and N is the midpoint of the other segment, CD, what means you're taking two equal lengths and cutting those equally in half. Well, what's the result? That means all the halves are going to be equal to each other. So halves of equals are equals, and that should be pretty obvious. That's why we tuck it into our postulate category. Another one is doubles of equals are equal. In other words, let's say then we're still given these two segments A, B, and C, D. We're still given that M is a midpoint and that C is a midpoint. M and N are midpoints of A, B, and C, D respectively. But what you're given in this second case is that you only know AM is equal to CN. So you know that half of the whole thing is equal to half of the whole thing of the other segment. And because of that, then if we double that length, we know then the double of those equals are also equal. So that means I can take AM, which is equal to CN, and I can then just immediately say, oh, then I automatically know that AB is equal to CD, because if I doubled those measures, they would equal the whole thing, which means doubles of equals are equal. And again, we're going to carry these two postulates with us into this last set of theorems. So let's take a look then at this last theorem. Once again, this doesn't have a title or a name to it, which means we're just going to follow by what it does. And its title is Equal Chords are Equidistant. What I mean by that, and this is what I'm saying in that statement there, is that if I were to produce two chords of equal measure inside of any given circle, so I have a circle down below, circle A, such that I've produced two chords, B, C, and D, E. What the claim is here is that they are equidistant from the center. Now, think about what it means when we use that term distance. Distance is that length, which is the perpendicular. That's why we have those two segments drawn in for us, AF and AG. They are perpendicular to each of the chords, BC and DE. So what we're claiming then is that if we're given chords of equal measure, they're equidistant from the center. In other words, that the length of AF will equal the length of AG. And that's what we're going to prove, is that those two segments there, AF and AG, are equal to each other. Let's take a look at that theorem, or at that proof. So we have the proof here, and I'm going to walk you through this proof, and we're going to find that we're going to make use of one of those postulates we just introduced on a few slides. So what we're given, again, is that the whole segment BC is equal to the whole segment DE. Now, recall then, what we're about to see is a use of just a previous theorem we just saw a couple slides ago. So just keep that in mind. We'll see, because AF is really part of a diameter and it's perpendicular to a chord, we know something more about point F and point G here in just a moment. Now, where we begin in our proof is actually with another construction. We are simply going to take point A, our center, and connect it to point B, and connect then point A also to point E as well. Let me redo that one. There we go. And what we form is a set of triangles there, that pair of triangles, and our goal is to prove that those triangles are actually going to be congruent to each other, because with congruence, we can bring our best friend CPCTC in, and with that we can prove then that AF and AG are equal to each other. So where do we begin? Well, we know that our newly formed segments AB and AE, they are going to be equal to each other. Why? Because those are radii of the circle, and by definition of radius, we know that those are going to be equal in length. Now, here's what we know next. AF is really part of a radius or a diameter, and AG is also part of a radius or diameter. And what we're going to find there is that with both of them being perpendicular to our chords BC and DE respectively, that means we can say AF officially bisects BC. In other words, F is a midpoint, and AG bisects DE. We can claim G is a midpoint because of a theorem we just proved a couple slides ago, which is that perpendicular diameters bisect chords, which means we can claim that with F being a midpoint, right, we know that this is going to be a midpoint, and that G is a midpoint. We can also claim that the halves of equals are equal. In other words, we can claim that all four, I should actually put double hash marks on those, all four of those segments, FC, FB, GD, and GE, are all equal to each other. But more specifically, I really just want to claim just one set of those sides we know to be equal, and that's specifically BF and GE. And the reason why I claim both of those is because those are part of the triangles that I'm trying to build to be congruent. Well, what that means for us is we have an equal pair of sides, actually two pairs of equal sides, and the angle AFB is right because we have we're given their perpendicular, that's the distance, and we already know that AGE is right, which then means we have our special case of congruence one more time. We have hypotenuse leg. Because our hypotenuses are equal, we have an equal pair of legs, and with the right angles in there, we know we have our special case hypotenuse leg. Now, what does that mean? We can invite our best friend, CPCTC, to the party, and that means we can claim our third pair of sides also must be equal to each other. AF is equal to AG, just like we wanted to prove in our setup. Now, this proof with our equal measured chords being equidistant from the center of our circle does actually have a true converse, which means you're going to see another proof on your homework assignment that involves the converse of this, essentially saying that if there are chords that are equidistant from the center of the circle, we can prove then they must be equal in length. And I'll go ahead and give you a clue on that one. We are going to use that second postulate that we introduced, which is doubles of equals are equal. Okay, doubles of equals are equal, because you're going to use that to your advantage, where you find F to be the midpoint, G to be the midpoint, and you'll be able to prove that BF and GE are equal, which means if you double those, the wholes then also must be equal, which means BC and DE would be equal to each other. And that's what you're going to be proving on your assignment, the 9.3. So we've come to the end of our lesson, looking at the relationships between arcs and chords and some information we can prove using those relationships. And as you notice, in all of these relationships, we used congruence, right? We use these pointy things, triangles, and arrive to congruence, actually arrive to conclusions that we can prove about these roundy things, right, with our circles. So be sure to hop over and take a look at that worksheet 9.3. If you do have any questions on that, please do not hesitate to email me. With that, be good and do good.